we mentioned before that for some angles it's very easy to calculate the sine and cosine. For example, for multiples of pi halves, we were quickly able to calculate what the sine and cosine were for those particular angles. But for most angles, it's not that easy to figure out what the relationship between the angle and the horizontal component, the cosine, and the sine are. So just having the angle, it can be difficult to find sine and cosine. Usually we're happy just to approximate them. But there are a handful of other cases where we can easily calculate the sine and cosine. And since we can do it easily, those are the cases that come up quite often in calculus textbooks. So let's review those so that you can have those memorized and be able to get the answer they're expecting you to get when you work these calculus problems. So there are really two special triangles that we're going to consider. The first one is the equilateral triangle. Now, equa means same and lateral means side, so the triangle where all three sides are the same. Now, you remember that the sum of the angles of a triangle has to be pi, or you probably remember it has to be 180, right? But I'm trying to get you to think in radians here. So since the sum of the angles has to be 180, and since this triangle has all three sides the same, then it must be that you could just rotate it and all the angles would line up again. So all three of these angles have to have the same measure. So if they all have the same measure and they add up to 180, then they've each got to be 1/3 of 180, which would be 60 degrees. Or in our radians, that would be pi thirds. So all of these angles are pi thirds. So 60 degrees and pi thirds, those are going to play a special role for us because we'll see in just a second that it's easy to calculate the sine and cosine for those. The other case is the isosceles right triangle. So in this case, we have a right triangle. So this angle is pi halves, or 90 degrees. And let's see, since the sum of the angles has to be pi, and since it's isosceles, that means two sides have the same length. So this will be our isosceles triangle. Then these two angles have to be the same. Let's actually give these two marks because they're different from the other. But okay, so these two angles have to be the same, and so that would be pi fourths and pi fourths there. So let's see how we can find sine and cosine for these angles by using these two special cases. So the first one let's look at is this equilateral triangle. What I'm going to do, we know that these three sides are the same. Let me cut it in half here with a perpendicular. So this is a 90 degree or a pi halves angle right here. So I'm going to cut it into two right triangles here. We already said that this angle's measure must be pi thirds, right, or 60 degrees. So if I cut this straight down, whatever length this is, let me call that length A. If I cut it straight down, then it's going to break this into two equal pieces. Both of them will have length A over 2. Okay, now also it's going to cut this into two angles, so two equal angles. Since the whole measure is pi thirds, each of these will be half of that, which is pi sixths. Or let's see, pi thirds and 60 degrees are the same. This one will be a smaller angle, it will be 30 degrees. Over here we'll have pi sixths as well, or 30 degrees as well. Okay, so what we have here is, let me just look at one side. We have a right triangle, and we've got a 90 degree angle there. Right triangles are a favorite because they obey the Pythagorean theorem. The Pythagorean theorem says, I'm not sure what this distance is, but the Pythagorean theorem says that if you take the sum of the squares of the two shorter sides, so in this case, a over 2 squared plus b squared, that's going to be equal to the square of the hypotenuse, or a squared in this case. Now a over 2 times a over 2 times itself, which is what this indicates, is going to be a squared over 4. So a squared over 4 plus b squared is going to be a squared. If I take a quarter of an a squared away from an a squared, I'll have 3/4 of a squared left, so I'll have b squared equals 3/4 a squared, or this length b is going to be equal to, let's take the square root here. We'll have the square root of 3 over the square root of 4, which is 2, times the square root of a squared. That will be essentially a there. So now we know that this is equal to root 3 over 2a. That's kind of handy. So it tells us that if we have an angle of pi thirds here, And if this happens to be 1, then this length will be the hypotenuse over 2, so that's going to be 1/2, and this will be the square root of 3 over 2 times the hypotenuse. If the hypotenuse is 1, like on the unit circle, then this is going to be the square root of 3 over 2. So remember that this horizontal is the cosine, so the cosine of pi thirds is 1/2. The vertical is the sine, so the sine of pi thirds is root 3 over 2. Of course, you could turn this picture on its side as well. So put it so that the long leg is down. And we already figured out that this angle was pi 6 because it was half of pi thirds. So if I turn it down this way, here's our pi 6, there's our hypotenuse of 1, here's our pi thirds. This length must be 1/2, and that one's root 3 over 2. So that tells us that the horizontal for pi 6, that's the cosine of pi 6, is root 3 over 2, and the vertical is 1/2. So the sine of pi 6 is 1/2. So we kind of got 2 for 1. We figured out the sine and cosine of pi thirds and pi 6 just from this special equilateral triangle. That's not too hard to remember, although I'll kind of show you a mnemonic here in a second for memorizing these. It's kind of fun to see that you can do it. It's all based on the Pythagorean theorem, which hopefully has been drilled into your head for many, many years. Okay, so next one we wanted to consider was the isosceles right triangle, where we had a 90-degree or pi halves angle here and 2 equal sides. So let me label this side A and that side A. And this length I'm not so sure about, but I can use the Pythagorean theorem to figure it out. We said these two angles would both have to be pi fourths or 45 degrees. Let's see, the Pythagorean theorem says that a squared plus a squared, the sum of the squares of the two shorter sides, is equal to the square of the hypotenuse. So we just have the same number here because it's isosceles, right? Both lengths are the same. So let's see, we end up with a squared equals c squared over 2. So a is basically c over the square root of 2. In particular, if we're talking about an angle of pi fourths or 45 degrees, if the hypotenuse happens to be 1, then these two shorter sides will both be 1 over root 2. Now, if you don't like having a radical in the denominator, then you've been well trained. We can get rid of it, though, if we multiply top and bottom by the square root of 2. So if you take the square root of 2 times the square root of 2, you just get 2. So you'll see probably both ways in any calculus textbook, depending on the graduate student that made the answer key, probably, or just how lazy someone's feeling. They won't always rationalize the denominator for you. They'll figure that you can do that and understand which ones are equivalent. So, okay, so we can actually figure out now that the cosine of pi fourths, the horizontal when you're on the unit circle, the cosine of pi fourths is 1 over root 2, or root 2 over 2. And the sine of pi fourths is also 1 over root 2. Okay, those two special triangles now helped us figure out how to get the sine and cosine of both pi 6, pi fourths, and pi thirds. So we can now go around the circle with a little bit more accuracy here. So what I'm going to do is at each of these special angles that we know, I'll just mark them here. Halfway, third, third, halfway, a third, just marking these particular angles. I'm going to write the angle, and then I'm going to give the sine and the cosine. Since the cosine is the horizontal, I'll give the cosine first, and then I'll give the sine for that particular angle. So we already said that when the angle is 0, it's all horizontal and no vertical. And now we know that when the angle is pi 6, that the cosine is root 3 over 2, and the sine is 1/2. Oh, by the way, the square root of 3 has got to be more than 1, right? So you can see that square root of 3 over 2 is bigger than 1 over 2. And that makes sense because if the angle's kind of shallow like pi 6, then you can see that the cosine, the horizontal, has to be longer than the sine, which is the vertical component. So that makes sense that that this should be the bigger one, right? That the cosine should be the bigger one. When we go over here to alpha equals pi fourths, then we can see that the sine and the cosine are the same because that's where we had that isosceles right triangle. They're both square root of 2 over 2, or 1 over root 2 if you're feeling kind of lazy. All right, and at pi thirds, this is really just the pi 6 case, though, reversed, right? Now it's the vertical that's tall and the cosine's kind of short. We have 1/2 and root 3 over 2. We can just keep going around here. Alpha equals pi halves. Then there's no horizontal. It's all vertical. Now it gets kind of interesting as we go over here. You can see that our horizontal component, we're going backwards. So when we're over here in quadrant 2, the cosine has to be negative, but the sine should be positive. Let's see. The first place that we get to is 2 pi thirds. That's this angle, and this angle is 3 pi fourths, and this angle is 5 pi 6. Let's figure out the sine and cosine in each case. This time we're going back, so the cosine's negative. It's just like this, right? We could actually reference what happens with pi thirds to figure out what happens with 2 pi thirds. We would say pi thirds is the reference angle for 2 pi thirds, if you like. So the cosine is negative 1/2. We're still going up, so the sine is root 3 over 2. At 3 pi fourths, we're going back and up, so the cosine's negative, negative root 2 over 2, but the sine is positive, positive root 2 over 2. And at 5 pi 6, we're going back root 3 over 2, right, and up 1/2. We could say that pi 6 is the reference angle for 5 pi 6. It tells us the distances we should go. We just have to give them the correct sign for the quadrant that we're in. Now when we get to this angle of pi, we remember that it's all horizontal. We're going back one step and no vertical, so the cosine's negative 1 and the sine is 0. Let's keep going along here. This angle is 7 pi 6. This angle is 5 pi fourths. And this angle is, let's see, 8 pi 6 would be 4 pi thirds, right there. Now again, to figure out what's happening, we can, for 7 pi 6, we can just reference pi 6. The only difference is now that we're in quadrant 3, we're going back and down, so cosine and sine are both negative. We're going back, root 3 over 2, and we're going down 1/2. At 5 pi fourths, we're going back, root 2 over 2, and we're going down, root 2 over 2. And at 4 pi thirds, we're going back 1/2 and down root 3 over 2. We've got the sine and cosine for each of these angles so far. Now at 3 pi halves, remember there is no horizontal, you're just going straight down 1, so the cosine is 0 and the sine is negative 1. And let's keep going here. This one is 5 pi thirds. So here's this angle, 5 pi thirds. And then we have 7 pi fourths, and then we have 11 pi 6 before we get back to 2 pi. But the sine and cosine for 2 pi are the same as for 0, aren't they? So at 7 pi fourths, now the cosine's positive because we're moving forward, and the sine is negative because we're going down. We're moving forward, root 2 over 2, and down, root 2 over 2. Oh, I forgot to do 5 pi thirds. We're moving forward 1/2 and down negative root 3 over 2, right? Here we're at 11 pi 6, we're moving forward more and down a little less than when we were at 5 pi thirds, right? These, forward, so that should be positive. So positive root 3 over 2 for the cosine, negative 1/2 for the sine. All right, so from just a few angles, we've been able to construct all of these.